Okay, so this is the second video for optics, and I'm focusing on the geometrical optics here. So here is the first question. You can pause the video. So they are referring to a concave mirror, which exactly behaves like a convex lens or converging lens, kind of like a magnifying glass. So the object is at the center of curvature of a concave mirror. The image form will be real, inverted, not inverted. So you can choose here A, B, C, D. So if we can use that simulation here, we can go to mirror, and this is a concave mirror. And the center of curvature is about here. Okay, so it means if that will be the center, and here you could make a circle. So here you can make a circle, and that will be the center of the circle. So you see when the object is beyond, okay, it's going to be inverted, real, and smaller. When it's just at that center here, it will be real, inverted, and same size. And if we move it inside here, it will be inverted, real, upside down. And if we go beyond the focal point, it's going to be virtual and upright. So playing with those, it helps, remember? So it's going to be real and inverted. Luckily, they don't ask for the size, so that's good. Okay, so then they want you to look at this figure here. And so you have light here, it's going to be refracted, reflected, okay? And then, so this is total reflection, and then it's leaving the medium. So first of all, if this is the medium, so you can pause the video, of course, but you see if you have a medium here and air, you see that light will burn toward the normal. So if you have a material here which is denser than air, it's always toward the normal. Okay, so it means alpha will be smaller than theta. So alpha smaller than theta, so it's going to be this one or that one. And then everything is symmetric here, right? Everything is symmetric. So we expect theta prime to be equals to theta. So the answer will be have theta prime, no, here. So answer is B. Okay, so here they talk about a convex mirror, and you want to change. It's a convex mirror, and convex mirror with a lens here in front of the convex mirror. We don't know exactly what's going to happen after, but it doesn't matter. So you have a convex mirror and a convex mirror and a convex lens. So what's going to happen is that they want to change the focal length of the convex mirror. So of course, changing the position of the lens is not going to change that. It's a property of the lens of the mirror. Focal length of the lens at B is not going to change the focal length of the mirror. Either it's the index of refraction or the radius. But when we talk about mirror, we never talk about the index of refraction. That will be a property of the lens here, right? So when light goes through a lens, it will be refracted. But it's not the case for a mirror. You could have refraction if you have the metallic part which is covered with a layer of glass, but it's very much complex, so we don't talk about that. So the only solution will be B. So you have to be very quick with that. But you can look at that here. So this is a convex mirror. Okay, so you see that it behaves like a concave lens, meaning the image is always virtual. Okay, it's virtual because it's beyond here. So it's virtual and it's upright. So it's like a concave lens. And if you change the radius, what you are doing, you are changing the focal length, right? So if you increase the radius, focal length will increase. If you decrease the radius, the focal length will decrease. If you change the diameter, it will make the image brighter because you're going to catch more. You're going to catch more rays if it's bigger. So it will brighter image or dimmer image. That's all. So the answer is this. And of course, you should stop the video. Okay, so let's go to the next question here. So this one is an easy one. Okay, you can look at the picture. So this is called the concave lens, or concave or diverging lens. What's going to happen to the rays? It will, obviously, it will diverge, right? So again, you can play with this. You can go to lens. You choose a concave lens, and you see how the rays are diverging. So that's why it's called diverging lens. And you see the image is always virtual. It's always virtual. Yeah. Okay, so that's an easy one. Visible light. Okay, so how can we explain refraction? So light, you can see light as a wave, or you can see light when light interacts with matter, depending on the frequency, but when it interacts with matter, it can behave like particles, right? Like photons, like particle waves. So what's happening at an atomic level is that the atoms of the dense medium absorb the photon and remit them. So denser is the material, more packed are the atoms, so it will delay even more. So the atom absorb the photon and then re-emit. So what's happening at the atomic level is that it's the electron, right? It's absorbed by the electron. They go to a higher level of energy, and then when they move back, they will emit that photon back. And it's not the nuclei, because to excite the nuclei, you need very, very high energy photons like X-ray or gamma ray. And so here we are talking about visible light. So it says visible light. So that's why we know it cannot be the nuclei. It's a little bit tricky question. Okay, so next one, of course, remember that you can always pause the video. So this one is just to make sure you know Snell's law, and also that you can do the computation, you know enough geometry, like simple relationship here, to do it without a calculator, right? So we have glass, so this is denser than light, and you take the normal here, so this is normal because it's perpendicular, and you have light going. So this is 45 degrees. So this angle here is always here, 45 degrees. So some of it will be reflected at the same angle, and some of it will be refracted toward the normal. So it's toward the normal, and this is 30 degrees. Okay, so we're going to use Snell's law. So this is refractive and index N1 and M2. So 1 times sine 45 equals N2 sine 30. So sine 45, you have to know that by heart, right? Square root of 2 over 2 equals N2 sine 30 is 1/2. By the way, it's given here. Boom, boom. And so it's going to be square root of 2, which is about 1.41. So the answer is here. So just to test how much you know about geometry, to make sure you can go fast without thinking too much. Okay, so let's do the next one. Okay, so this is interesting. Let's see what's going on. Because that's just to test the reading comprehension. And it always helps to make a drawing. So it says here you have N1, N2. N2 is larger than N1. And this, they say, we don't know. And then it's going to be reflected. Okay, so it's going to be closer to the normal here. And they say, also we know the reflected angle, if the angle of reflection is already measured. So that's what you have to figure this out. So we know this angle here. But we know because it's a reflection that they're going to be equal to each other. So this is known. This is known. That's you want to know. So what is missing to solve? So equation is this. And this is 1. R is 1. Okay. So this you know because it's the same as the reflected one. This you don't know. And this you don't know. So you need this, right? If you want to find out. So the angle, you need to know this one. So answer is B. Okay. So again, you should stop the video. So in the next one, they are talking about reflecting beads. So what are reflecting beads? No, it's called retro-reflecting beads. So some material that you use for sign, for example, on the road. Okay, so you have those signs here. Okay, so people can see them with a headlight. You have them also here as lines on the road, and they reflect the light. So when you are driving here, you have the light from your car, and this here will become visible because it will reflect light. Okay, same thing here. So they are called retro-reflecting beads, little beads here that make up the material. Okay, I don't know if I have a picture of the beads. Maybe not, but you see how it's being reflected in the same direction as the incidence ray. Okay, so these are little beads here. Here you have a picture of them. They are very tiny, very small. Okay, so they ask you which one will make sense. So light comes here. So this one is not possible because as it's gonna enter the bead, it has some refractive index here, larger than the air, so it should be refracted, and it's not happening there. So A is no. A, you see, it's refracted, but it gets away from the normal, which is not possible. If you have a material denser than air, the ray will be refracted toward the normal. So B is not. Yes, this one makes sense, right? You see how it's being totally reflected here. So you have a critical angle, and here it's refracted toward the normal. C, yes. This one doesn't make sense because if you trace the normal here, it's refracted away from the normal. So D, no. C. And it makes sense. Okay, so the answer is C. So this is called retroreflective bead. Right? So let's do this one. It's a so it's like a virtual image, right? When you look at something in water, it will look closer to the surface than it is in reality, right? So if I have something like this, and this is because of refraction. So let's say this is the water here, and you have a fish inside. So you have a fish here. Maybe I'm going to place the fish further down here. And you are here. And you are looking at the fish. You see a ray coming from the fish here. So it goes, let's say it's going in this direction. Now it goes from dense to less dense. So it's going to be refracted this way. So it seems that the back of the fish is somewhere over there. And then here also, of course, all the ray goes in all direction, but this one will be caught by your eyes. So maybe you have one here. Okay, and it's also going to be refracted away. Something like this. So where they meet, it's going to be here, right? So it will meet at a distance closer. My drawing is not great, but it will be closer. So it will be above the actual fish. It will be above the actual fish, right? It looks like it's a mirage, right? And so you can look it up at your textbook to a better image. My picture is not great, but the height here, the height will be the real height there, which is 4 meters. So 4, and you divide by 1.33. So 1.33 is 4/3. So you multiply by the reciprocal. So it's going to be 3 meters. So it will be 3 meters below the surface. 3 meters below the surface. So this question is not clear, but it will be 3 meters below the surface versus 4. Okay, so there will be 1 meter above the actual fish. So it's not below, it could be this answer here. So it will be above. So 1 meter above the actual fish or 3 meters below the surface. Okay, so there is a typo here. Okay, so here again with the lens, the distance from the arrow to the lens is greater. Then the focal length. So you can pause the video, but it's a converging lens. So the image will be real and inverted. Real and inverted. Okay, so again, you can play with that. If you have a lens here, converging lens, as long as I'm here in this zone, okay, so the image is real inverted. So if it's twice the focal length, it will be real inverted, same size. And if it's inside here, twice the focal length and twice the focal length, it will be larger. And you go here, it will be virtual. So here they want to know, so it's again with the retro-reflecting lens. So retro-reflecting lens, not lens, beads, okay, little sphere of plastic or glass, must be plastic here, so it's very small. And they want to know how many wavelengths you can fit in. So you should pause the video. So there is a principle in wave optics. If the wavelength is larger than the opening could be a lens or a bead, then the light will bend around. So you're going to have diffraction. So in that case, it doesn't work very well. But if the wavelength is way smaller than the opening, which is a bead, so then it will not be refracted too much, diffracted too much. It will go inside and being reflected as we want here. So anyway, they don't want you to talk about the physics. They just ask you to do the computation. So you have to be careful when you have a question like that. Don't think about the physics too much, just do the computation. So they want you to know, you can pause the video, but the wavelength times the frequency is the speed of light, okay? Because the frequency is 1 over the period. So this is meter, this is second, meter per second is, yes, a speed. Okay, so the wavelength will be 3 times 10 to the 8 divided by the frequency. Scientific notation, you're going to get a minus 7 meters. Okay, so it's going to be 0.3 micrometers. Or 300 nanometers. So anyway, 3 times 10 to the negative 7. How many of them fit? How many wavelengths? So how many of them fit in this bead here? So this is the bead, the diameter. How many wavelengths? So this is 1 wavelength. So how many of them? So you just divide, right? Times to negative 5 divided by 3 times 10 to the negative 7. So 3 goes into 5, 1.7. 10, so you go up, so 10 to the second, and there is no unit here. Okay? So it means the wavelength is way smaller than the size. So light will not diffract too much. Because otherwise, if it's not the case, if the wavelength is larger than the opening, light will do something like this, right? It will bend around. We don't want that. We want light to go inside and be refracted. I think that's all I have. So that was a short video. No, there is one more. So the object is 30 centimeter in front of a thin converging lens. So 30 is larger than 10. So it should be a real inverted. It should be real inverted and smaller. I think there is a mistake again. Right, let's see. So if you have a converging lens here, converging lens, see if my object, so it will be here, it will be the same size. So the focal length is 10 centimeter, so that will be 20. So if it's 30, it will be real, inverted, and smaller. So again, there is a mistake here. Let's see. It will be real, inverted, and smaller. There's a typo. Okay, that's it for today.